is part 3 of Griffiths 2.2.3, Applying Gauss's Law. In previous videos, you have used Gauss's law according to different kinds of symmetries. So when you had spherical symmetry, you drew a spherical Gaussian surface. When you had cylindrical symmetry, you drew a cylindrical Gaussian surface. And the other symmetry that we're going to use frequently is just Cartesian symmetry. Okay, so I am going to walk you through example 2.5, where we have an infinite plane. That plane has some surface charge density sigma, and I want to know what's the electric field generated by that plane. Okay, and you can see here that drawing spherical or cylindrical Gaussian surfaces is not going to be appropriate because we don't have anything that looks like those surfaces in the problem. Instead, what we're going to do is we're going to define a Gaussian pillbox. Okay, that pillbox is going to be a little box that lives on our surface. Okay, so I'm going to draw a three-dimensional object, right, that is centered on my surface. Okay, so this bottom line right here is on my plane, and the dash bits are below the plane, and the solid lines are above the plane. Okay, I could draw a perfect side view of that, and using the same colors, I would get something that looks like this. Okay, where again that red line is this line right here. Okay, so the question then becomes, what is the electric field? All right, and the tool that we're going to use is Gauss's law. In integral form, Gauss's law tells us that the surface integral of all of the electric flux must be equal to 1 over epsilon naught times the charge enclosed by that surface. Now, you can see that I can fairly easily calculate the charge enclosed by that surface. I have a surface charge density sigma. My box has a top area of A, so the total charge that's enclosed by my surface becomes A sigma. All right, now I have to figure out what is the electric field dotted with all of my surfaces. Okay. So we know by symmetry that the electric field is pointing out above and below my plane. So what I need to do is I need to evaluate that dot product with all of my surfaces of my box. I have a lot of surfaces, but I'm going to be creative about doing this. I'm going to go ahead and draw this again just a little bit bigger. I have some plane here. I have my box. And I'm going to evaluate what the flux is through this top area here. And then there is an equivalent area underneath that I need to worry about. And I also have to worry about all of the sides, right? But I think I can rationalize that the side contributions are going to be 0 because the sides are going to be pointed in, let's go ahead and call this the X, Y, and Z directions. The sides are all going to be in the XZ plane or the YZ plane, and the electric fields are always going to be in the Z direction. So those dot products become zero because they're perpendicular to each other. So what I need to do then is calculate the integral over my green surface and add that to the integral over my purple surface, right? And then what I said with words is that, you have all these other surfaces, all the other sides, but that contribution is equal to zero. Okay, and all of that equals 1 over epsilon naught times A sigma in this case. All right, well, I've chosen my surface to have a constant height, right? And I've chosen the surface to be pointed in the same direction as my electric field. So I'm able to, I won't use the colors anymore, I'm able to say that this is the magnitude of E dA. And since we've done this a couple times before, I'm going to be a little quick about it. That's the magnitude of E pulled out of that integral because it's constant and it's pointed in the same direction, plus the magnitude of E over my second surface equals 1 over epsilon naught times A sigma. But the integral of my surface is just the total surface area of that chunk of section 1, or of green, right? That becomes E times A, okay? And then the integral of my second surface, it's exactly the same size, so it becomes E times A. I get 2E, my A's cancel, 1 over epsilon naught sigma, and then my electric field then points 1 over 2 epsilon naught sigma. I have to put my direction on at the end, but my direction was implied given this, right? And that's in the z-hat direction. Okay. Commonly, we'll refer to this as the n-hat direction, 2 epsilon naught sigma n-hat, which is just the direction normal to that surface. But since I drew this coordinate system, that's okay to do. All right, so that's how you use Gauss's law with Cartesian symmetry.